Well, we have been progressing toward mastery of projectile motion problems, but we're not there yet. We have seen so far a basic vertical flight, dropping or launching from the bottom without any horizontal motion. We have seen this type where you're launching horizontally and letting it hit the ground. And we've seen motion from the ground and hitting the ground again a little bit later, with also including some X motion. So that's where we've come, and now we still need to get the more general situation where we have from a height to a lower elevation, or from a lower elevation to a higher elevation, which will be the same basic idea. So we're just going to analyze this first one here. This one is analyzed the same way. So let's get into this. As our example, we're going to launch this from a height at V0 at angle theta, height H, maximum height Y max, and then a range. So we're going to get all this understanding from it. Of course, we have to be given some of these quantities, so we will. And note, though, that the initial and final speeds, so the initial and the final speeds, how are they going to compare? Is there symmetry all the way through? No. You know that if we go straight across, that the speed over here is going to be the same as the initial speed. But it's having more time or distance to fall. So the initial and final speeds are different. Now the range is Vx times the total flight time, as before. The maximum height occurs when? What happens here? What's true about the motion? That's right, Vy is equal to 0. So we'll consider that. And then I want to make note that I am going to be using my starting point as Vy0. It's totally valid. I'm sorry. My starting point as Y0 equals 0. It's totally valid to, on the ground, call that Y is equal to 0, but that's not Y0. So Y sub 0 is our beginning point by definition. I like to call it 0, then down here is a negative value. You don't have to do it that way. You can start with this being 0, this being positive, but that's just the way that I consistently do it, and we'll model it. Okay, so Y is equal to 0 at the beginning of flight. And then let's let the height be 10 meters, the initial velocity 16 meters per second with an angle of 30 degrees. Let's solve for the total flight time, maximum height, and the range. Okay, well, for the flight time, we are going to use equation 5. It is the only equation robust enough to include everything we need and solve for t. We have everything else. So let's look at how this plays out. The final vertical position is minus 10. The initial is 0, as I said, by definition. Vy0 is V0, 16, sine of 30 times time minus 1/2 g is 5. So there's our equation. Now let's simplify that. There it is. And let's put it in this form. And what does that look like? You guessed it. This type of projectile problem results in a quadratic formula expression, a quadratic form of equation. So we need the quadratic formula. Negative b plus or minus the square root of b squared minus 4a times c over 2a. And that gives us this, or this simplified expression, resulting in 2.4 or negative 0.8 seconds. So hopefully you're comfortable with the quadratic formula. Then let's just take a brief look at what we have here. The answer we're looking for, the time from this moment to the end of the flight, is this. It's the 2.4. Okay, so that's the answer. We're starting at 0 seconds and going to 2.4 seconds of flight. But what about this? That is the negative 0.8 seconds. If we complete this in the past, we project this backwards, 0.8 seconds ago, we would have had to have launched this projectile in such a way that the actual initial conditions here are met at the end of this little segment. And if all that's true, it would have been 0.8 seconds ago that we launched that. Okay, so that's the significance of the other solution. Now let's solve for the range. Vxt, V0 cosine of theta t, which is 16 cosine of 30 times now our understood flight time at 2.4, and that gives us 33 meters. Let's get the maximum height. Again, at the maximum height, Vy is equal to 0. So let's go ahead and use that, and to get us the time, this expression will give us the time, recognizing that this is 0 at the top. So the uptime, or the time to get to the top of the flight, will emerge from that. So Vy0 equals gt. So t is Vy0 over g, 8 over 10, gives us of 0.8 seconds to go from here to here. So don't get that confused with this 0.8 seconds. It's a different 0.8 seconds based on what I chose here. Okay, so at the top of the flight, 0.8 seconds. So now we can get the maximum height with our equation 5. And we know that we're already at 10 meters. So I'm going to include that this time in my y0. So 10 plus Vy0 t, 8 times t, minus 5t squared. Knowing that our time is 0.8 seconds, we can plug that in. We get 10 plus 6.4 minus 3.2, giving us 13.2 meters. That's our height. In this case, it'd be from the ground all the way up. If we start here, it would just be 3 more meters, 3.2 meters to the top of the flight. Now, instead of using these two expressions, we could have just done this equation. In fact, that would be my preferred way to do it. I kind of wanted to brute force our way through this process with these two expressions, but we can solve for the height, setting this equal to 0, easier than what we just did. And we don't need this time. The time we just had, we didn't even need it. All we needed is Vy0, and we could solve for h, knowing that Vy is equal to 0 at that point. So the nice thing about this is there's always more than one way to solve the problem. And as long as you latch onto one valid way, one legitimate way, you should be good to go. So that'll conclude our basic outline of the essential projectile motion problem types.